more improper integral identification type of stuff. So question 21, we go from -8 to 1 of 1 over, or dx over x to the 2/3 power. Well, if you look at this guy right here, we've got x, he's in the denominator. The one thing he can't be is 0. So anytime x equals 0, we have a potential issue, and that actually occurs on our interval. So at this point, we would say that we're going to have an improper integral at x equals 0. And that's really all there is to it. We're going to have an infinite discontinuity at that location. Since we have an infinite discontinuity, we have an improper integral, and we take those steps to solve. Okay, we're going to evaluate this guy down here, or state if it diverges. So looking at it, we are going to have an issue when we get 0 in the denominator, which is going to occur at 3. So we're going to reset this to go from 0 to 3 of dt over 3 minus t plus 3 to 6 dt over 3 minus t. So keep in mind when we're working this out that both of these integrals are going to evaluate out the same way. Both of them evaluate out the same way. The only difference is going to be what we evaluate from and to, okay? So we'll work just one, and whatever we get for just that one, we're going to use for the second one, okay? Also keep in mind that we are going to have that infinite discontinuity at 3. So if we're going to be super technical, we would say that this is the limit as b approaches 3 from the left of the integral from 0 to b dt over 3 minus t plus the limit as b approaches 3 from the right of dt over 3 minus t, the integral of that, and then we're going from b to 0, b to 6. There's your setup, and I'm just going to go ahead and work one of these integrals real quick. If we look at the integral from, say, 0 to b of dt over 3 minus t, remember that this is a setup for the natural log. So if we were to let u equal 3 minus t, then du is equal to -1 dt, which we would move that -1 over, and we would have this. So the integral we're solving out actually has this shape with a negative sign in front of 1 over u du. So that would integrate to natural log, the negative natural log of u 3 minus t. And we're going to evaluate that from 0 to b, and we're going to look at only the absolute value part of that, okay? Shouldn't be a big deal in this case, but you never know. So the first guy would evaluate out as negative natural log of b minus t. And remember, we're going to allow b be equal to 3, all right? So, whoops, shouldn't be b minus t, it should be 3 minus b. And then minus negative natural log of the absolute value 3 minus 0. Okay? So when I look at this, if I can put a 0 in here for this b, if I can put a 0 in there, because that's what I'm approaching according to the, oh, sorry, if I put a 3 in there, because that's what I'm approaching. 3 minus 3 is 0, and this takes us towards negative infinity. Okay? This guy over here, when I put that in, I get the natural log of 3. And so already I can tell, based off of what's going to happen, that this guy right here, this infinity symbol, is going to throw off the entire rest of the problem. So I'm not even going to do anything else. I'm just going to say, you know what? This guy diverges. He doesn't have a limit at all. And so we're done. okay? And again, it's because as we put as we put a 3 in for this b, we get the natural log of 0, which you can't have that. But we're talking about close to 0, not at 0. And just real quick, if we were to graph this, the natural log graph looks like that. So what's happening as you get close to 0? You're falling towards negative infinity. If you don't approach a specific number, then your limit diverges. Okay, on 23, we want to try and figure out if this integral converges or diverges, but we're going to use the comparison test, because if we look at this guy, this is not the most user-friendly integral to try and sort through. So what we can do is we can compare this to another integral, and just think about this for a minute. If I've got 5 plus cosine x over square root x, what would that maybe be similar to? I chose 1 over the square root of x. Okay. This is a similar sort of thing that's going on. And what we're going to do is we're going to check for divergence. Now, I don't know if there's a reason to check for divergence or convergence. I mean, it's hard for me to tell right off the bat what's going on. But here's one thing I do know. If I pick a function and that function diverges, okay, so let's say this is 1 over square root x. I don't know, just saying. And the function above it, if it's less than a second function, if the red function diverges, then the brown function also diverges. All right. On the flip side of that, if we can find a function that approaches a specific point and converges, and then we can find another function that's less than that, okay, then if the pink one converges, then the blue one has to converge, okay? So what we're trying to do is kind of look for some different things. Well, 1 over root x is actually less than the highlighted function here. So what I'm going to do is I'm going to check for divergence. If 1 over x diverges, this guy diverges because it's bigger over the entire interval than 1 over x is. So 1 over x is definitely the easier problem to work out, all right? So here we go. B is going to approach infinity. We're going to look at the integral from 1 to b of x to the negative 1/2 power. Integrate that, and we get the limit as b approaches infinity of x to the 1/2 over 1/2, which is like saying 2x to the 1/2. And we're going to evaluate that from 1 to b. So it's where we stop minus where we start. Well, remember, b is approaching infinity, so we're looking at 2 times the square root of infinity. That matches this brown equation right here that matches the red equation right here, where it's diverging. It doesn't approach anything at all. And since it diverges, this guy right here also diverges. And that's how the comparison test works. We compare 2 functions together to determine if it's possible to figure out convergence or divergence. So there you go. There's a comparison test for this example.